Well, welcome back. We are ready to complete our theory of the MOSFET. We call this the transmission theory because the transmission parameter plays a key role in this theory. So recall, we have an expression for the current that involves the transmission number of channels and the Fermi functions in the two contacts. In this lecture, we're going to allow the transmission to go between 0 and 1. We're not going to assume it's 1 as we did for the ballistic MOSFET. We're going to allow for the presence of some scattering of the carriers in the channel. So we have a simple relation between the transmission, the mean free path for backscattering, and the channel length. We are going to assume, just for simplicity, that the mean free path is independent of energy. So you might think of it as some average mean free path of the electrons with the different energies near the bottom of the conduction band for an N-channel MOSFET. And as we did for the ballistic MOSFET, we will first apply our theory to the linear regime, then to the saturation region, and then we'll use the virtual source model to smoothly connect these two regions. So let's begin with the linear region. So you recall that we developed a theory when the transmission was 1 for the ballistic current in the linear region. And this is what we obtained. You might guess that all we need to do is to multiply now by the transmission, and we can include the effects of scattering. Well, that's correct. That's all there is to it. So we don't have to work out any new integrals. We simply multiply by the transmission. So this is our expression. This should treat the MOSFET from the ballistic to the diffusive limit, depending on what the channel length and mean free path is. So we have a theory, a transmission theory of the linear region of the MOSFET. Now, let me plug our expression for the transmission in our expression for the current. And then this is what we get. Now, if you look at the quantity in the brackets, that may look familiar to you. We've seen that before. That, in fact, is simply the mobility in a large bulk semiconductor due to scattering. Lambda naught is the mean free path for backscattering. Vt is the thermal velocity. So our final expression is very simple. Our linear region current is just W over length, channel length, plus mean free path, times mobility, times charge in the channel, times drain to source voltage. So you can see we've corrected the very traditional model simply by replacing the channel length by the channel length plus the mean free path. So, remarkably simple change, and allows us now to treat the linear region current from the ballistic to the diffusive limit, from the traditional to the ballistic limit. Now, it turns out that's not going to be the most convenient way for us to write the result. We're going to write the result in a mathematically equivalent way. We're just going to rearrange terms a little bit. So if I look at this expression, and if I pull the W out front, divide by channel length, and then multiply by channel length inside the brackets, then I can rewrite this expression in a different way. Recall that we know how the mobility due to scattering is related to the mean free path. So if I put this together, you should be able to convince yourself that we can write the linear region current in this form. Inside the brackets here, we have 1 over the mobility due to scattering. That's a well-defined quantity. And 1 over the mobility, the ballistic mobility. That's something that we encountered when we discussed the ballistic MOSFET. So in the more general case, both the ballistic mobility and the diffusive mobility enter into the current expression. Well, we're going to write the final linear region current in this form. We're going to put those quantities together, and we're going to define something that we call an apparent mobility. 1 over the apparent mobility is simply 1 over the mobility due to scattering, and plus 1 over the mobility, the ballistic mobility. So that's an apparent mobility. If we go to the ballistic limit, very short channel lengths, then that apparent mobility will approach the ballistic mobility. If we go to the diffusive limit, very long channel lengths, many mean free paths long, that apparent mobility will approach the diffusive, the traditional mobility. And if we're in between, we'll get something in between. Okay, let's work a quick example. Let's estimate the apparent mobility for a 10 nanometer channel length, something that might represent current day technology. The mobility due to scattering, or the mobility that you would deduce from a long channel MOSFET in this technology, might be about 250 centimeters squared per volt second. The ballistic mobility is well defined. We can compute the ballistic mobility for this 10 nanometer length MOSFET. First of all, we have to compute the unidirectional thermal velocity, and that's easy to compute. If we put that together, we deduce a ballistic mobility of about 230 centimeters squared per volt second, close to the actual diffusive mobility. That means when we put them together and compute the apparent mobility, this is the mobility that the MOSFET would seem to display when we measure its IV characteristics, we would find that the apparent mobility is about 120 centimeters squared per volt second. Less than the diffusive mobility and less than the ballistic mobility, less than both of them, about half of either one of those. So this device clearly operates squarely in what we would call the quasi-ballistic regime. It is not at the ballistic limit. It is not at the diffusive limit. To describe a MOSFET like this, which is representative of current day technology, we need to use an apparent mobility that accounts for the ballistic effects and the effects of scattering both. All right, now just before we proceed to the saturated current, let's look a little more at the linear region current. The current is conductance, channel conductance times drain to source voltage, or we could write that as channel drain to source voltage divided by the channel resistance. Well, we have an expression for this current. We can deduce what the channel resistance is. It'll have two terms, one involving the diffusive mobility and one involving the ballistic mobility. Well, when we put that together, you can see the ballistic mobility has a channel length in it. So we're going to get two terms. The first term is the traditional diffusive resistance. It scales as the length of the channel. If we make the channel twice as long, we get twice as much diffusive resistance. The second term involves the ballistic mobility. It is independent of channel length. Okay, so we deduce that if we measure a MOSFET, deduce its channel resistance, there will be a term that scales with the channel length, and there will be a term that is independent of channel length. By experimentally extracting the part of it that scales with channel length, we could measure the mobility. And that, in fact, is what people do. Okay, let's go to the saturated regime now and develop a transmission theory for the saturated current. Now, you might think that we would just do what we did for the linear region current. That is, we would take the expression that we developed for the ballistic MOSFET, and we would multiply it by the transmission in the saturated region. Well, that's a reasonable guess to make, but it turns out that that's not correct. And to explain why, we have to look a little more carefully at what's going on inside this MOSFET. Specifically, let's look at the virtual source, where we've been focusing our attention all throughout this course. So at the virtual source, one thing that's very special about the virtual source is that in a well-designed transistor, the total mobile charge at the virtual source is determined by MOS electrostatics. It's basically minus the inversion gate capacitance times VGS minus the threshold voltage. Okay, so MOS electrostatics keeps that inversion layer charge constant. Now let's look at the currents that are flowing inside this MOSFET. There are electrons that are injected from the source over the barrier and into the channel. they give us a current that I'll call I plus of 0. X equals 0 is the location of the virtual source. Okay, if we look at what comes out, the drain and constitutes the saturated current, that's simply transmission times the current that was injected, I plus at the virtual source. Okay. But in general, there will be some backscattering. So some fraction of the current that's injected will return to the source and not contribute to the drain current. Okay. The positive current will be carried by electrons that have a positive velocity. The negative directed current will be carried by electrons that have a negative velocity in the x direction, the direction of the channel. Let's look a little more closely at the virtual source at the top of the barrier, and let's think about the consequences of MOS electrostatics. So we have an injected current, a positive current that is carried by electrons with positive velocities. We have a backscattered current directed in the negative x direction that is carried by the electrons that have a negative velocity. We also know that this backscattered current, I minus at the virtual source, is simply 1 minus transmission times I plus. It's the part of the injected current that backscattered and returned to the source. Well, we can put these together and we can deduce that the ratio of the number of electrons with negative velocities to the number of electrons with positive velocities is simply 1 minus the transmission. Okay, so that's what scattering does. Gives us a relation between the number of electrons with positive velocities and the number of electrons with negative velocities. You can see that if we're ballistic and the transmission is 1, then this ratio will be 0. There will be no electrons with negative velocities. On the other hand, if we have very strong scattering and the transmission approaches 1, this ratio will be 1. And we'll have equal numbers of electrons with positive and negative velocities. That would be the long channel limit, the diffusive limit. Okay, so now we can return to our problem of deducing what the saturated current is. MOS electrostatics requires that the sum of the positive directed electrons and the electrons with negative velocities, their sum is always the same, maintained by the gate voltage in MOS electrostatics, and we've just figured out what their ratio is. So we could solve for the number of electrons with positive velocities. It would be the total number maintained by MOS electrostatics divided by 2 minus transmission. Okay, so this tells us what the number of electrons is. The numerator is determined by MOS electrostatics, and the denominator comes from the backscattering that occurs in the channel. All right, now we can deduce the drain saturation current. So we inject a current I plus from the source into the channel. That's width times Q times the number of electrons with positively directed velocities flowing at the unidirectional thermal velocity. Okay, what comes out the drain, or what gives me my drain current, is transmission times I plus at the virtual source. But we know how to relate the number of electrons with positive velocity to the charge at the top of the barrier controlled by the gate voltage in MOS electrostatics. If we put this all together, we see that the drain saturation current is not transmission times the ballistic current, but it's transmission divided by 2 minus transmission. That extra factor comes in because no matter whether the scattering is weak or strong, we have to enforce the consequences of MOS electrostatics that the charge, the total charge at the top of the barrier is maintained constant. All right, so we've derived the results. We've been a little more careful. We see it's not what we might have guessed. There's an extra factor that we have to be careful from in the denominator here. It's not transmission times the ballistic current. It's transmission divided by 2 minus the transmission. Okay, so we've done what we set out to do. We have developed a theory for the saturated current, the drain saturation current, which includes the effects of scattering. Let's write it this way. The current is width of the MOSFET times mobile charge at the virtual source times what we'll call an injection velocity. The injection velocity we've just deduced is transmission divided by 2 minus transmission times the unidirectional thermal velocity. So it's always a little less than or equal to the unidirectional thermal velocity. So this injection velocity is going to play an important role in our thinking about nanoscale field effect transistors. Let's look just a little, take a brief look at this injection velocity. The traditional velocity that we would have under saturated conditions would be the saturated, high field saturated velocity that we would measure in a bulk semiconductor. And the velocity saturates there due to strong scattering. That's not what we find at the nanoscale. In the ballistic case, we found that the velocity, the appropriate velocity to use, was the unidirectional thermal velocity, about 1.2 times 10 to the 7th centimeters per second for electrons in N-channel silicon MOSFETs. Let's refer to this as the ballistic injection velocity. More generally, what we've just seen now is that the injection velocity in the presence of scattering is transmission divided by 2 minus transmission times the unidirectional or ballistic injection velocity. So it's always a little bit less. All right, let's take an example and take a look at measured data. We've seen previously how we can compute the ballistic current. So we can compare the measured data to the ballistic current for this 30 nanometer channel length extremely thin SOI silicon N-channel MOSFET. Okay. When we do that, we find that the on current is about 70% of the ballistic limit. Now, the ratio of the on current to the ballistic on current, our theory says, should be transmission divided by 2 minus transmission. From that, we can deduce that the transmission is 82%. All right. So it's even higher than the ratio of the current, the measured current to the ballistic current, and it's actually reasonably close to the ballistic limit. Let's look at the injection velocity for this 30 nanometer channel length silicon MOSFET. The transmission is 82%. The unidirectional thermal velocity is 1.2 times 10 to the 7th centimeters per second. So the injection velocity for this device is about 0.84 times 10 to the 7th centimeters per second. All right, distinctly less than the unidirectional thermal velocity or the ballistic injection velocity. So that's how some typical numbers play out for typical MOSFETs these days. So we have developed now expressions for the linear region current in terms of the transmission, and expressions for an expression for the drain saturation current in the presence of scattering related to the transmission under saturated conditions. Now, one thing you'll note in doing these kinds of analyses is that we'll find that the transmission under saturated conditions, high drain voltage, is higher than the transmission under low drain voltages in the linear regime. Now, why is that? We might expect that the transmission would be lower under high voltage, because under high voltages, the electrons gain more energy and they have more ways to scatter. But we find that their transmission is higher. So what's going on here? Well, let's take a closer look. In the linear regime, we have a simple expression for the transmission. It's mean free path divided by mean free path plus channel length. The physical picture in an energy band diagram is an electron is injected from the source. If it backscatters anywhere on its path towards the drain, there's a chance then that it can return to the source and not contribute to the current. Okay? So the entire length of the channel matters for backscattering. Now, if we look under high drain bias, and in a properly designed field effect transistor, we'll find that there is a region near the virtual source where the electric field in the x direction along the channel is low, where the height of the potential barrier is strongly controlled by the gate voltage and weakly influenced by the drain voltage. That's a very short region, a region, I write it as script L here, which is just a small fraction of the channel length, and we'll see how small in the next lecture. We write the transmission T in the saturated region not as mean free path divided by mean free path plus the channel length, but mean free path divided by the length of this critical bottleneck region. If the electrons can get across that short region without backscattering, then even though they scatter in the high field region where they've got a lot of energy, the electric field is high there, the electrons will rattle around some, but they will exit through the drain and contribute to drain current. So under high drain to source bias, scattering only matters in this critical bottleneck region, which is some small fraction of the entire channel length. For that reason, the transmission increases under high drain bias. So the region, the critical length of the channel over which the scattering determines the drain current is the entire channel length under low VDS, but is only some small fraction of the channel length under high VDS. That's why the transmission is higher. Now, we should point out then that if we find that we have a MOSFET that is operating near the ballistic limit, we should realize that does not mean that there's no scattering in the channel. There could be quite a lot of scattering in the channel. What it means is that electrons have a good probability of getting across this very short bottleneck region. Then they might scatter quite a lot, but they're going to exit from the drain. So we can operate near the ballistic limit with currents near the ballistic limit in the presence of significant amounts of scattering. So that's important to realize. Now, another question that people sometimes ask is, mobility is a parameter that we measure on long channel MOSFETs or we measure in bulk silicon. Does mobility have any meaning in a nanoscale MOSFET? Well, the way to think about this is that mobility is related to the mean free path for backscattering. Backscattering in this critical bottleneck region, this very short region near the vertical source, is determined by the mean free path. So for that reason, the mobility does, in fact, have a strong influence on the on current of a MOSFET under high VDS conditions. So mobility is a very important parameter. If we find ways through strain or whatever to increase the mobility of the material, we can expect an increase in drain current in very short channel transistors. Now, the mean free path, this mean free path is the mean free path under low VDS, or the mean free path that we would deduce in a long channel length MOSFET. But the mean free path near the drain can be much, much shorter because the electrons there have a lot of energy and a lot of different ways to scatter. Okay, so we can summarize. We have our IV characteristics. We have now a simple expression for the current in the linear regime. It depends on this quantity we've introduced called the apparent mobility, which involves both the mobility due to scattering and the ballistic mobility. In the saturated regime, we've seen that we can take our traditional velocity saturation expression and simply replace the high field saturated velocity in bulk silicon by this quantity we call the injection velocity. And the injection velocity is related to the transmission under saturated conditions and the unidirectional thermal velocity. So, with those simple replacements of our traditional theory, we can describe very short channel MOSFETs, in fact, all the way to the ballistic limit. So, traditional MOSFET theory, All we need to do to describe short channel devices is to replace the mobility by the apparent mobility and the high field saturation velocity by this quantity we call the injection velocity. You might ask, why is it so simple? And to answer that question, remember way back in Unit 2 when we talked about the physics of how transistors operate and why transistor characteristics look like this. And we explained that in terms of energy band diagrams. The gate voltage and the drain voltage modulate the energy barrier, and by pushing that energy barrier down, we get more current. The shape of this IV characteristic, as we explained back in Unit 2, can be explained simply in terms of energy band diagrams and manipulating heights of potential barriers with the gate voltage. That gives the shape of the IV characteristic. The transistor characteristics, the traditional transistor model describes that shape. In very short channel devices, we have ballistic and quasi-ballistic transport. We have to account for that, but it doesn't change the shape of the transistor characteristics. It only changes the magnitude of the current, and with these two simple replacements, we can get the right magnitude of the current. All right, so that's our transmission theory of the MOSFET, and we've really done what we've set out to do in the course. In this unit, we will talk in the next lecture about revisiting our virtual source model, and that'll be very quick and easy to do, and then we can make use of that virtual source model in the subsequent lecture. So we'll continue this discussion in the next lecture.